So this is our second video on solutions. And so here we're going to start to talk about ways of expressing concentration. How do we expect the concentration of a solution? When you make a solution, you dissolve a solute up in a solvent. Okay, how much? You have to have a way of expressing the concentration. In other words, how much solute per given volume of solvent or given volume of solution. All right, so the first that we're going to talk about here is mass percent. All right, and mass percent is exactly what it sounds like. It's a percent by mass. In other words, it's the mass of solute divided by the total mass. And of course, what's the total mass? The mass of the solute plus the mass of the solvent, right? So mass of solute divided by the mass of solute plus solvent. Maybe I should have an extra set of parentheses around there. Alright, but it's the mass of solute divided by the total mass times 100 to convert it into a percent. Alright. Mole fraction is almost the same thing, except there's two differences. It's moles instead of mass, and we don't multiply it by 100 to convert it into a percent. It's left as a fraction. So mole fraction is the moles of solute divided by the total moles. Okay, so that would be moles of solute divided by moles of solute plus moles of solvent. Okay, so almost the same. Well, not really the same thing at all. But it's this. This is mass, and this is moles. Okay. Okay. Now, molarity, you should have seen this before in Chemistry 1. Now, molarity is abbreviated with this uppercase m, not to distinguish it from molality, which is a lowercase m. Okay, so molarity is moles of solute per liter of solution. Okay, so it's moles of solute per liter of solution. And molality is moles of solute per kilogram of solvent. Molarity is uppercase m, molality is lowercase m. A subtle but very important distinction between these two. Now, you might know that water has a density of 1 gram per mil or 1 liter per kilogram. And yet these are not the same thing, because this is per volume of solution, and this is per unit solvent. So what's the difference? Let's say when you make a solution. What do you do when you make a solution? First of all, you typically use a special type of flask called a volumetric flask. Okay. You use a special type of flask called a volumetric flask. Okay, which a volumetric flask measures one and only one volume. Now, when we say something is graduated, it has lots of markings on it, like a beaker or a graduated cylinder or something like that. Volumetric flask only has one mark on it. So let's say we have a volumetric flask. It's going to look something like this. Okay, there will only be one mark on the entire flask. Alright, and let's say we're dealing with a 1,000 ml flask, which is equivalent to 1 liter. Okay, so when you measure this up, when you fill it up to that mark, you'll have 1 liter of solvent. So let's say we want to make a 1 molar solution. So a 1 molar solution What is that? That's 1 mole of solute liter of solution. So let's say we wanted to make, for example, 1 molar sodium hydroxide, let's say. Then we would weigh out our sodium hydroxide, which is usually in the form of pellets. We would weigh that out, add it to our flask. Then we would add water. We would say water's our solution, water's our solvent, and then we'd add water up to the mark of the neck. In other words, what we're doing is we add enough water to make 1 liter of solution. Notice I did not say we were adding 1 liter of water. Okay, very, very important, a subtle but important distinction. We're adding enough water to make 1 liter of solution, not 1 liter of solvent. We're not blindly adding 1 liter of water. We're adding enough water to make 1 liter of solution. Well, why is that so important? This is because you don't know the ratio. You don't know the mole ratio or the mass ratio between solvent and solute because we didn't keep track of how much water we added. The only thing that we know here is the ratio between moles of solute and volume of solution. That's the only thing we know. Why is this so commonly used? Because it's convenient. When you go in a lab, it's typically easier and requires less equipment to measure a volume than it does to measure a mass. Okay? And the molar solution, one more time, and the molar solution, what you know is the ratio between moles of solute and liter of solution. Okay? But you don't know the mass ratio or the mole ratio between the two because you don't keep track of how much water you add or how much solvent you add. I keep using water as an example. So when we make, back to this, so when we make the 1 molal solution, now this is different. Now we're adding 1 kilogram of solvent. So if we wanted to make the 1 molal solution, we would take 1 mole of our solute and we would add 1 kilogram of solvent. So now we know how much solvent we added. So we know the mass ratio between solvent and solute, or the mole ratio between solute and solvent. Okay? Let's talk about how we convert between some of these methods of expressing concentration units. All right, so let's say we have an 8%, we have a solution of ammonia that's 8% mass, it's 8% ammonia by mass, and it has a density of 0.9651 grams per ml. So you want to calculate the molality and the molarity of the solution. Okay. So what do we know? It's 8% ammonia by mass, and it has a density of 0.9651 grams per milliliter. We will calculate the molality and the molarity. So let's assume 1,000 grams of solution. That's just a convenient number to work with. We could assume 10 or 100, or I'm going to assume 1,000. So we know that it's 8% ammonia by mass. So let's start out by taking 8% of 1,000 grams. So 8% of 1,000 grams is 80 grams of ammonia. So then we convert that into moles. You should know how to do that. Divide by the molar mass, or what I did here is multiply by 1 over the reciprocal. So 80 grams divided by 17 grams per mole is 4.70 moles. Okay, 4.70 moles. Um, so how much solvent was present? See, I'm first calculating the molality here. Remember, molality is moles of solute per kilogram of solvent. So we know it's 8% ammonia. Well, if it's 8% ammonia, then it's 92% water, assuming water is the solvent. All right. So, or we could simply take the 80 and subtract it from 1,000. We assumed 1,000 grams total. 80 grams of that was the ammonia. So we subtract that and we found out we have 920 grams of solvent. Well, 920 grams is 0.92 kilograms, right? One more time, molality is moles of solute per kilogram of solvent. So we're going to take our 4.7 moles divided by 0.92 kilograms, and you get 5.11 molal. Okay, so our solution is 5.11 molal. So we assumed the mass, and we took a percentage. We took the percentage. We know it's 8% ammonia. It's 8%. 8% of the 1,000 grams is 80, divided by a molar mass of ammonia is 4.7, okay, and divide that by the mass of the solvent, okay. Okay, same problem, except now let's do the calculation for molarity. Okay, so let's assume 1 liter of solution. Okay, so just like in the previous example, we assumed 1,000 grams. Now we're going to assume a liter of solution, which is 1,000 milliliters, right? So we knew what the density was. It is stated in the problem 0.9651 grams per milliliter. So let's take our 1,000 mils times 0.9651 grams per mil. Is total mass is 965.1 grams. You can probably guess where we're going next is to take 8%. Now we work it like the previous problem. You take 8% of the 965.1 and that's 77.2 grams. And then you divide that by the molar mass of ammonia. So you turn out you have 4.54 moles, which is basically a 4.54 molar solution, because we assumed a liter solution. And one more time, that uppercase M, that molarity, is moles of solute per liter solution. Okay. Now, if you know the molarity, or if you're trying to calculate the molarity, or if you're trying to calculate the molarity into another unit, you have to know the density. You have to know the density. Because when you made the 1 molar solution, you didn't keep track of how much solvent was added. So one more time, in a molar solution, all you know is the ratio between moles of solute, and liters of solution. Okay. You have to have a way to convert, if you're going to convert molarity into another unit, you have to have a way to convert the volume into a mass. And the only way to do that is the density. Okay. So if you're going to convert molarity, if you're converting from molarity into another unit, or if you're converting another unit into molarity, you have to know the density. So you can convert the volume to the mass. Okay? Because one more time, molarity is per unit volume. Molality is per unit mass. Alright. So, colligative properties. This is where we're going with this, is when you dissolve a solute in a solvent, you change the properties of the solvent. Okay, you interfere when you dissolve a solute, you interfere with those molecular forces of attraction in the solvent, and you make new forces of attraction. There's new forces of attraction between the solute and the solvent. You're disrupting the solvent. You change the properties of the solvent. Okay, so in what ways does this change? And your colligative properties, they depend upon the number of solute particles in solution. So, in other words, the more solute we put in there, the more these properties change. So what are some of your colligative properties? The first is vapor pressure lowering. Okay, when you dissolve a solute, or rather, yes, when you dissolve a solute, you lower the vapor pressure of the solvent. Okay, you lower the vapor pressure of the solvent. You raise the boiling point of the solvent. Okay, so the boiling point elevation is your second. Freezing point depression. In other words, you lower the freezing point. You lower the freezing point of the solvent, and then there's this something called osmotic pressure. We'll talk about that when we get there. All right, so vapor pressure lowering. One more time, vapor pressure lowering. You lower the vapor pressure of the solvent. Okay. Boiling point elevation. You raise the boiling point of the solvent. Freezing point depression. You lower the freezing point of the solvent, and you change the osmotic pressure. We'll talk about what osmotic pressure means. So let's talk about we'll go through these one by one. Let's talk about the vapor pressure lowering first. Okay. We'll talk about the vapor pressure lowering first. So we're going to talk about two cases. First of all, we're going to talk about a non-volatile solute, and then we'll talk about volatile solute. Okay. So when we say something is volatile, what does that mean? It means that it evaporates readily, or it has a high vapor pressure. So like hexane, for example. Now, non-volatile then is the opposite of that. So a non-volatile substance does not evaporate readily and does not have a vapor pressure of its own. So for example, if you're dissolving salt up in water or sugar up in water, those are non-volatile solutes. They don't have any vapor pressure of their own. Okay. So this follows what's called Raoult's law, which says that the pressure of the solution is equal to the mole fraction of the solvent, right? So that's the mole fraction of the solvent. X represents mole fraction. Okay, times the vapor pressure of the pure solvent. Right, so mole fraction of the solvent, vapor pressure of the pure solvent. So let us work an example here. Alright, so at 25 Celsius, the vapor pressure of water is 23.8 torr. We want to know what is going to be the vapor pressure of a solution made by dissolving 45 grams of glucose, which has a molar mass of 180 grams per mole, in 100 grams of water. Okay, so what we have to do here is calculate the mole fraction of the solute, or mole fraction of the solvent rather. So we're going to have to first figure out, all right, how many moles of glucose do we have, and how many moles of water do we have. So let's first figure out the glucose. Okay, so 45 grams, That's a lot. That sounds like a lot. In fact, that would probably fill up 150 ml beaker. But glucose is pretty heavy. It's 180 grams per mole. So 45 grams divided by 180, that's only a quarter of a mole. All right. How many moles of solvent do we have? 100 grams of water. Just divide that by the molar mass of water. That's 5.55 moles. Okay. So the water, in terms of number of moles, we have a whole lot more water than we do glucose, right? So we want to calculate the mole fraction of the water. So that's the moles of water divided by the total moles. So that's 0.55 moles, 5.55 moles divided by the sum of the 5.55 and 0.25. This comes out to be 0.96. Okay, so the vapor pressure drops to 96% of what it started with, the 23.8 torr. So 23.8 torr times 0.96 is 22.8 torr. Really, so the vapor pressure doesn't really come down that much, from 23.8 down to 22.8 torr. Okay, and that's because, one more time, these colligative properties, all of them, depends upon the moles. All depends upon the moles of the solid. Has nothing to do with the mass of the solid. It has to do with the moles of the solid. Okay, so that's why we had to take the 45 grams, divide it by 180, convert it into moles. Okay, if we were dealing with a lighter substance, let's say, then that 45 grams would be a greater number of moles. This would be a bigger number, and the mole fraction of the solvent would come down, and the vapor pressure would come down a little bit more. All right, so let's do one more case. Now, what if we're mixing two volatile liquids together? What if we're mixing two liquids? Classic example, let's say we were mixing benzene and toluene. That's the example that I'm going to use here. Well, each of those substances has its own vapor pressure. In other words, the toluene is going to lower the pressure of the vapor pressure of the benzene, and the benzene is going to lower the vapor pressure of the toluene. So that calculation that we just did in the previous example, we're going to have to do that twice and then add the two numbers together, right? So the vapor pressure, we'll just call our two components A and B. All right, so the vapor pressure of component A is the same as in the previous example, is the mole fraction of A times the vapor pressure of pure A, all right, and the vapor pressure of component B is the mole fraction of B times the vapor pressure of pure B, right? So we have, like I said, we have to do this calculation twice, right, and then add the two together to get the total pressure. It's like I say, A lowers the vapor pressure of B, and B lowers the vapor pressure of A. So we have to do it twice and then add the two components together. Okay, so like I say, the example I was going to use here is benzene and toluene. Okay, so benzene has a vapor pressure of 95.1 torr, pure benzene, and pure toluene has a vapor pressure of 28 torr. So let me ask you this question. First of all, which has the higher, which is more volatile? Whichever one has the higher vapor pressure, right? The more easily a substance evaporates, the higher is going to be the vapor pressure. So vapor pressure of benzene is higher than that of toluene. The benzene evaporates more readily. So when we mix the two together, first of all, what kind of answer is going to make sense here? like I said, the benzene is going to lower the vapor pressure of the toluene, and toluene is going to lower the vapor pressure of the benzene. So our final answer should be a number between 28.4 and 95.1. Okay. So, what is the vapor pressure of a solution that contains half a mole of benzene and half a mole of toluene? Okay. So you should be able to see that the total number of moles is equal to 1. This is kind of a shortcut problem because the total moles is equal to 1, so the number of moles is the mole fraction. Okay, so what's the vapor pressure of pure benzene? 0.5 times 95.1 is 47.6 torr. Okay, right, the vapor pressure of benzene has come down, or the benzene component, it's come down, and the toluene is 0.5 times 28.4 is 14.2, and we add those two together, and you get 47.6 plus 14.2 is 61.8, okay, and this number is, in fact, between 28.4 and 95.1, like we thought it should be. Now, like I said, don't get confused here. This was kind of a shortcut problem because the number of moles adds to 1. Okay, if that were not the case, then we'd have to divide to get the mole fraction. Let's do a quick example. Let's say we had let's say we had 0.50 moles of benzene and 1.50 moles and 1.5 moles of toluene. So now we'd have to go through and calculate the mole fractions, right? So the total moles is 0.50 plus 1.50 is 2, correct? So what's the mole fraction of the benzene? The mole fraction of the benzene is 0.50 over 2.0, right? And what is that? 0.25. Okay. And the mole fraction of the toluene is now 1.50 over 2 is equal to 0.75. Okay, and these are the numbers that we would use down here in this calculation. So if we were going to recalculate this, we'd say 0.25 times 95.1 and 0.75 times 28.4. Okay, just don't want you to get lulled into a false sense of security and think that the number of moles is what you use here. It's not, it's the mole fraction. This was just a convenient example. Okay, but note that the sum of your mole fraction should always add to 1. 0.25 and 0.75 add to 1. All right, we'll stop here. This is the end of part 2.